Hi students, welcome to my lectures on chemical reaction engineering. In the last class, we have learned about how the zero order reaction will behave, how the velocity is constant irrespective of the concentration. Today we are going to learn about finding non-zero order of the reaction. Because if you remember, this is the equation. Minus Ra is equal to minus dCA by dt is equal to K Ca power n. K is the rate constant, n is the order of the reaction. In today's example, let us find out the order of this particular case. Okay, in the similar analogy like a marathon. Okay, a person is running to cover a distance of 20 kilometers. He started at 20th kilometer, comes to the 0 kilometer. And the analogy we use here is compare with that of a distance with a concentration. Example, I am finding out the order of a reaction in a batch reactor. Initially I have kept 20 moles per liter as an initial concentration. What happens during the reaction? The concentration of 20 mole per liter will come down to the 0 mole per liter, for example. And during the process, how I can say what kind of order the reaction that is. Okay, let us go with the process. A person, starting with an example of the marathon. A person, he started at 20th kilometer and come down to the 0 kilometer at certain time period. Here I have plotted on the y-axis the distance covered by the person, and on the x-axis the time he has taken to cover this long distance. And from the 20th, let us say he has started from the 20th kilometer, and from the first 30 minutes he has covered the 5 kilometer distance. Okay, a person has taken 30 minutes to cover the distance of 20 to 15 kilometer, which is 5 kilometer, and I have simply drawn a line connecting these 2 points, and I have evaluated the slope. Slope is nothing but the velocity. That means dd by dt, distance by time, is called my velocity of a person. So he because the slope will be negative because of the curve. Okay, because of this, it's a negative slope, a line with a negative slope. Initial velocity, that means during this distance from 20 kilometer to 15 kilometer, the velocity he has maintained is 0.16 kilometer per minute, for example. And for the next 5 kilometers, that is from 15 to 10, he has taken almost 30 to 90, which is 60 minutes. That means initial 5 kilometers he has covered in 30 minutes. Next 5 kilometers he has taken 60 minutes. So the slope at this point, dd by dt at 2, which is nothing but 0.08. Okay, that means for the second 5 kilometers he has velocity 0.08, which is less than 0.16. Similarly, for the next 5 kilometers, 10 to 15, he has taken almost from 90 to 180. That means almost he has taken 90 minutes. First 5 kilometers he has taken 30 minutes, next 5 kilometers he has taken 60 minutes, next 5 kilometers has taken 90 minutes. You can see now the speed of the person is getting reduced. Okay, now the speed is 0.05 kilometer per minute, and the last 5 kilometers from 5 to 0, almost he has taken 180 minutes to the 300 minutes, even more 120 minutes he has taken. You can imagine, the speed, the starting speed of the person is higher, the ending speed of the person is lower. Okay, you can see for the zero order reactions in my earlier lecture, the speed everywhere it is constant. Every 5 kilometers he covered a distance of, every 5 kilometers he has taken 30 minutes of time. But here only at the initial stage he has taken 30 minutes, and subsequently for the next 5 kilometers the time even got increased. That means the speed of the person is higher at the initial stage, and the speed of the person is the lower at the final stage. These kind of situations are called non-zero orders. Zero order velocity is the same everywhere. For the non-zero orders, the velocity will change. Okay, Now let us apply this analogy. Imagine this is not a distance, this is the concentration. Okay, instead of distance, imagine this is y-axis as a concentration term. I have taken a reactor, batch reactor. I have kept some reactants inside the batch reactor. I have started the reaction to happen. The reaction, the initial condition of the reaction is initial moles is 20 moles per liter. Okay, the reaction started with 20 moles per liter of the reactant A, and slowly what happens with the progress of time, the concentration will drop. Okay, the first concentration drop 20 to 15, it has taken 30 minutes. For the next 15 mole per liter to 10 mole per liter, the reaction has slowed down. That means it has taken more time, 30 to 90 minutes it took. And from 10 to 15, even 90 to 180, 90 minutes it has taken. Similar, apply the analogy of marathon. Okay, that means the speed or rate of the reaction is higher at the initial stage, and speed or the rate of the reaction is lower at the final stage. This is this classical example of non-zero orders. Okay, let us find out what kind of order is this by fitting the curves. But imagine this is what for non-zero orders, the velocities are not same. I mean, depending upon the distance, if it is at 50, depending upon the concentration. Okay, if the concentration is higher, the velocity is higher. If the concentrations are lower, the velocities are lower. So that's what the typical, kind of non-zero order reactions. Okay, the speed of the man, you can see the first slope is higher than the second, than the third, than the fourth. That means dd by dt1 is higher, and next slope is lower. That means velocity is higher at the initial stage and lower at the final stage. Similarly, if you consider the concentration, the speed of the reaction or rate of the reaction is higher at the initial stage and lower at the final stage. Let us proceed to find out what order it is. I know it is a non-zero order, but what order it is? Let us go ahead. Now take these slope values. It is not actually straight line. I have to connect the things with the curve. Okay, because velocity varies everywhere. But between these two points, I have taken a straight line. But in fact, you have to take a curve and take a slope at this point. Okay, but for you to make it understand easily, I have connected these 2 points with a line. In fact, it is entirely a curve. Okay, let us see. I have 4 different slopes here. That means this particular slope is at average concentration of 15 plus 20 by 2. This particular slope, that means this velocity of the reaction happens at concentrations between 10 and 15. Okay, this particular speed of the reaction happens between the concentration 5 and 10. This particular speed of the reaction happens between the concentration 0 and 5. So that's what I have done here. The first slope at this average concentration, the second slope at this average concentration, third at this, fourth at this. Okay, now I know the data dCA by dt and Ca average concentrations. Now what happens is I plot dCA minus dCA by dt on y axis and average concentrations on x axis, and you can see this is the data plot that was generated with respect to this. That means from this data what I can say is higher is the concentration, higher is the slope, lower is the concentration, lower is the slope. That means now the speed of the reaction, that means higher is the concentration, higher is the speed, lower is the concentration, lower is the speed. Now the entire speed of the reaction depends on what concentration it is. Now simple, I have to fit this line dCA by dt on y axis, concentration is on x axis. Now I fit a power equation. Using Excel you can easily do that. Provide the data and power, fit a power equation for it. From the power equation I got K, the constant, rate constant is 0.019, the concentration power 0.63. That fits, this line fits this data well. Okay, then from this what is the order of the equation? Now anything power to that of a concentration, summation of all the concentration, and here we have only one reactant, A gives rise to B, with the one reactant, now Ca power 0.63. So now what is the order of this equation? 0.63. Order could be fraction, order could be negative, order could be anything, right? Non-zero. So now it's a classical example of non-zero order. This is what the beauty of finding the order of the reaction using differential method of analysis. In other methods like integral methods, half-life methods, and everything is also fit for the line, but using this differential analysis, I mean, you can able to relate this to the real life example like marathon. Okay, hope you have understood well, and let us meet in the new lecture. Thank you very much.